Okay. All right. So welcome to the last week. Before I get into what we're covering this week, which is essentially integral transforms, I've been thinking about how to end class. And given that the world's on fire, and you guys have been working really hard with difficult stuff, and we've covered, or I will have covered, everything that I wanted to cover. I've decided on the following deal. What I need you to do is to finish out this week, turn in the next homework. I will update grades. I got the last homework this morning, so solutions for homework 6 have been posted. I will today I'll update your grades, and then assuming you turn in homework 7, what I'll do is just make the final optional, which means that you can take your grade after homework 7's turned in. So I'll grade the homework. I'll drop a homework if that's allowed, and whatever grade that is, if you're happy with that, take it and run with it. If you'd like to improve or potentially improve your grade, you can take the final, but it won't hurt your grade. So I think I did this last term with my other classes. If you're getting an A and you're happy with the A and you don't want to take a final, then great. If you're getting a B and you're happy with the B and you don't want to take the final, great. If you're getting a B and you want to try for an A, take the final, but then if you blow the final, it's no big deal. Okay, everybody understand the situation? Okay. The only requirement that I'm making of you this so that we do cover this stuff, which is important, especially if you're moving forward with your physics careers, is that we finish out this last week. So I am asking that you turn in homework 7. Okay. All right. Fantastic. If you have any questions, make sure that you talk to me about that. Okay, and I'll get the grades updated as soon as I can today. Now, today we're going to start a week of integral transforms, and this is kind of, for me, it's why we take this class. I mean, there's lots of stuff that is kind of cool, some of which you've seen, some of which you haven't, but it's all kind of leading to this week. Sadly, we could spend a whole term on this, but kind of we're building up the techniques in order to use this. And that is the idea of integral transforms. Integral transforms are important for a number of reasons. The main reason, I think, is that it allows us to take something that might be a difficult problem in one space, one kind of problem space, maybe that's time domain or physical domain, transform it into frequency space, solve it there, then transform it back. Oftentimes these problems are easier in that space and you can transform it back. So we'll be looking at transforms and inverse transforms. These also cover a class of problems, which I hinted at. It's in the last comment on the solutions for the last homework, of what are called integral equations. Integral equations are essentially integral versions of differential equations, right? So, and in order to solve those, you need to define a kernel that's inside the integral, and that kernel is what's being multiplied what's multiplying f of x. You might have something like f of x is equal to the integral of something times f of x, right? That's an integral equation, just like a differential equation is x double prime is equal to something times x, right? And so there are certain functions that solve that. There are certain functions that solve these particular integral transformations. So this has a lot of applications, obviously, in physics, and you've probably seen some in quantum, signal processing, optics, differential equations, things like that. So the first thing that we're going to look at then, we'll just look at the general case and then move to Fourier transform. And in fact, we'll use Fourier transform as an example. Integral transform. So I already have that up there. Sorry, get that away. Okay. This is just the intro part. We'll do an example. And as an example, we'll look at a definition for the Fourier transform. And I should point out that there are different normalizations for the Fourier transform. So depending on the textbook that you see, you might see different normalizations. But the one that Arfken uses, which is pretty common, is say G of omega is equal to 1 over square root of 2 pi times the integral from minus infinity to infinity of f of t e to the I omega t dt. All right, so this is the general Fourier transform. And basically what this is allowing us to do, somewhat like what we were doing last week, we're taking something that's a function of t and writing it as a function of omega. Okay. One of the things that you can think of in terms of Fourier transforms is with the Fourier series, we took a periodic series and we broke it into, we were able to represent that as a bunch of sines and cosines. Right? Fourier transform, the reason why it's important for signal processing is that it allows us to do the reverse of that in effect. It takes a signal and it tells you what are the important frequencies that are there. Right? If it's a pure frequency, if it's an infinite cosine with one frequency, then you should get one spike at that frequency. We'll see if it's a truncated wave, you'll get harmonics. If it's a combination of waves, you'll be able to pick out each of those frequencies, and that's what leads to things like power spectrum analysis, right, and discrete Fourier transforms, which you've probably used in practice. This isn't the only Fourier transform that we can use. We can also have the cosine and sine transforms. And that kind of, as we'll see in the in-class example, those are, you use those if the symmetry is advantageous for that. So this is square root 2 over pi, sorry. So square root 2 over pi has the integral from 0 to infinity f of t cosine omega t dt. And the sine series is the obvious similar case where you have sine omega t dt. 8.2 to 8.3. Okay. All right. So again, all we're doing is we're trying to take something that's written in one space and then transform it into another space, see if it's an easier problem, or see if the underlying physics is a little more obvious in that space. So one typical example is to look at a Gaussian and transform the Gaussian. So in this case, we'll have our f of t is equal to e to the minus a squared t squared. And here we'll just look at the general Fourier transform. So g of omega, so now the function in terms of frequency, is equal to 1 over root 2 pi times the integral from minus infinity to infinity, e to the minus a squared t squared, e to the I omega t dt. If we look at that, and whether you did this explicitly or not in quantum, this was a lot of trying to solve some of the intervals in quantum, is realizing that you can write this out as minus a squared t squared plus I omega t dt, and then you complete the square, right? So if we complete the square, for the exponential. At least that was certainly a lot of Griffith's version of the quantum text. So if you complete the square, you can show that minus a squared t squared plus I omega t is equal to minus a squared t squared minus I omega t plus omega squared over 4a squared minus omega squared over 4a squared. So that equals, we combine everything, minus a squared times t minus I omega, it's an I, over ta squared squared minus omega squared over 4a squared. Okay, that doesn't look like that saves us much, but that means that we can rewrite this integral a little more fruitfully. This also suggests that we shift the integral. We shift t to t plus I omega over 2a squared. When we do that, we can rewrite this integral g of omega as 1 over the square root of 2 pi times e to the minus omega squared over 4a squared times the integral from minus infinity to infinity of e to the minus a squared t squared dt. Okay. That's basically using the fact that we completed the square and then shifting this. Now the shift in coordinates is it's a little opaque, but essentially what we're doing is we're realizing that when we do this, is that our interval is essentially taking us on a contour interval out to some large t. We let t go to some big value t, eventually infinity. And we're shifting down so that we have t to the minus I omega over 2a down here, minus t minus I omega over 2a over here, and minus t over here. What this means is that we can basically represent this as this integral along the x-axis. And the final piece to this is to just make this a little cleaner. Let z be equal to at, then this integral from minus infinity to infinity of e to the minus a squared t squared dt squared is equal to 1 over a times the integral from minus infinity to infinity of e to the minus z squared dc. But that's a Gaussian integral, and that has a value of pi over a. So if we put that back into our expression over here, we have that our Gaussian in the time domain is equal to g of omega times 1 over, if we collect all of these terms, root 2a times e to the minus omega squared 4a squared. So kind of interestingly, this transform of a Gaussian gave us a Gaussian, but this is the difference here is that the peak of the Gaussian in time space becomes a lot wider in frequency space. Again, that's because we're trying to represent something that is essentially finite, or most of it is finite, with a bunch of frequencies that gets wider. Okay, so this is an example of I don't know if it's a straightforward example, but it is an example of what we can do with these Fourier transforms. And I'll get to something a little more concrete or a little more straightforward in a bit. Are there any questions before we go on?
And
I've not done anything really physically. Adrian, do you have a question?
yeah, in the integral right
Yeah,
above square root of pi over a, you have a dt squared. Why is it dt squared?
probably a typo. Where's dt squared?
The red. Uh,
Oh, that's a typo. Thank
okay.
you. Yeah, thank you. Okay, so all we're doing is we're trying to pick out essentially a dependency that isn't necessarily obviously when you're just looking at it. This will become more obvious when we look at other problems. And one of the great things, one of the reasons why we would use this, well, let me ask you. We've taken things and used Fourier series to represent discontinuous functions as continuous functions, right? Why would we use the Fourier integral and the Fourier transform instead? What's the difference between the functions in a Fourier that we use in Fourier series versus the functions that we see in, say, Fourier transform? You can kind of see it with the example that we just did. What is one thing that a Gaussian is not?
Discontinuous?
So it is continuous, but think about the functions that we represented with the Fourier series. What was one of the conditions of those functions? It's almost an implicit condition rather than explicit, although technically it's explicit. We get so used to using it that we don't really remember that that's part of it.
Is that they're finite?
Finite in what sense?
Well, for a series that has to be on an interval, and this is from negative infinity to infinity.
It has to be on an interval. Not only that, it has to be on a repeating interval, right? So when we use Fourier series, we're talking about a periodic function. We're looking at a piece of it, but we're assuming that it's going to connect here and connect here and connect here. That's why we have things like the Dirichlet condition. The only reason why we have a Dirichlet condition is because we've got, say, a step function, but we know that if we go one step over, there'll be another one and then another one, right? So we use the Fourier series for something that's periodic. The Fourier transform is looking at something that's not periodic. Okay. All right. Oops. All right. We have other transforms that we'll look at. And here I just want to just do this by way of introduction. The general case, as I've already mentioned, is g of, say, alpha is equal to some interval f of t times some kernel dt, right? And the functional form of that kernel essentially tells you what kind of transform that you have. So, for example, we have the Laplace transform, which is what we'll end the class with. And that's g of alpha is equal to the integral from 0 to infinity of f of t times e to the minus alpha t dt. This is the thing that will allow us to take ordinary differential equations, second order ordinary differential equations, and transform them into algebraic sequences. The Hankel transform, what do you think that does? You have f of t. What do you think the form of the kernel is for a Hankel form transform?
Hankel function. Like the Bessel function, Neumann function thing.
Say it again.
The Bessel function.
Yes, yeah, exactly right. So the way to think of this, right, is that the Fourier series represents an expression of function that is not periodic. And the Hankel transform does the same thing, but not for sines and cosines, but for Bessel functions and Hankel functions and Neumann functions. And then there's the Mellin transformation, which is similar to the Laplace transformation, but we won't cover that in class. Okay. So as I said, one of the things that we're doing here is representing something that's not periodic in some other space. So what we'll spend the next couple of classes on is doing a dive into Fourier transforms. And that's most of what's in the problems in chapter 20, I think. Well, the first part of chapter 20. So we'll start with the Fourier integral. And again, some of these definitions vary from textbook to textbook. So don't be surprised if you see something somewhere else, say Wolfram, and the normalization or the definition is a little bit different. But here our transform is 1 over 2 pi times the integral from minus infinity to infinity times d omega minus infinity to infinity f of t times cosine omega t minus x dt. What we'll normally see, though, is the exponential form. There are actually several forms of this. 1 over 2 pi times integral from minus infinity to infinity of e to the minus I omega x d omega minus infinity to infinity f of t e to the I omega t. Okay. In terms of, so that's just the integral. Our first stab at the actual transforms, there are a couple versions of this. There's the exponential form. So g of, say, k is equal to 1 over 2 pi to the 3 halves. This would be for a three-dimensional transform times the integral f of r times e to the I k dot r, and then over that three-dimensional space. The inverse of that would be representing f of r, again with this 2 pi 3 halves, and that root 3, or that power, the 2 pi to the 3 halves comes from this three-dimensionality. And now this is the integral of g of k e to the minus I k dot r d cubed r. There are also cosine and sine versions of this. Again, typically it comes from the symmetry of the problem. We usually write this as f sub c of x is equal to the square root of 2 over pi times the integral from 0 to infinity g sub c of omega cosine omega x dx. And then the obvious similar one for the sine series. And you would use one or the other depending on whether you had an even or an odd function. Okay. I'll give you a chance to finish writing that down, and then we'll do an example. And then you'll do an example, and then I'll do an example. We'll see where we are with time. the whole point here for now is, can we represent something that's not periodic, but also might be discontinuous as a function? That's one goal of the Fourier transform. The other is to move from one space to the other and make our problem simpler. Okay. All right. So let's look at an example. So in this example, we're going to take a we're going to do this transform for a discontinuous but non-periodic function. So in this case, we have f of x, we'll say 1 when x is between -1 and 1, and 0 when it's outside of 1. In other words, right at -1, 1. Okay. Now, we've done this for Fourier series, assuming that it's periodic, right? And then we could just make up that sines and cosines. What we're saying is, this is all there is. How can we represent this then as a function? All right. So, since this is not periodic, we want to use the Fourier integral. And essentially what we're doing is similar to finding the C sub n's or the B sub n's and the A sub n's, right? So g of alpha is equal to 1 over 2 pi times the integral from -infinity to infinity times of f of x. Since we're using the exponential function, expansion, e to the minus I alpha x. We could, if we wanted to, use the sine or cosine, right? So we could use c.5. Here we're using the exponential, mostly because of the way that the symmetry of the problem. So this equals -1 over 2 pi times the integral from -1 to 1, because it's all 0 outside, times e the I alpha x. That's equal to 1 over 2 pi times e to the minus I alpha x over minus I alpha, evaluated from -1 to 1. So that's 1 over pi alpha times e to the minus I alpha minus e to the I alpha over minus 2i, just by making some, noticing some useful substitutions. So this ultimately is sine alpha over pi alpha. Okay. So that's great, that's g of alpha, but we're not done, right? What we want is to be able to represent f of x, right, as a function, right? So, or evaluate f of x. So f of x is equal to the integral from -infinity to infinity of sine alpha pi alpha e to the I alpha x dx. So I want to take a moment just to think about what we're doing here. This is the non-periodic analog to what we do with Fourier series, right? When we do the Fourier series decomposition, right, we are given some function. We're assuming it's periodic. We find our a sub n's, right? Then we put those a sub n's back into a summation, right? But and that gives us our function, right? As a combination of sines and cosines. So what we just did with doing this integral for G alpha is get what we need to put into our integral so that we can represent f of x dx. All right, so if we evaluate this is 1 over pi, excuse me, times, or the integral from minus infinity to infinity, sine alpha times cosine alpha x plus I sine alpha x, just to make things a little easier. Alpha, oh, sorry, this is the alpha. All right, we're trying to solve for x, not integrate over x. All right, so this is equal to 2 over pi. This is, so we recognize that this becomes even, so we can do 2 over pi times the integral from 0 to infinity of sine alpha cosine alpha cosine alpha x over alpha d alpha. And it's because sine alpha over alpha is even. And then all that's left is evaluating. This integral 0 to infinity of sine alpha cosine alpha x over alpha d alpha is actually pretty interesting. It becomes pi halves times f of x. So this becomes pi halves for x, absolute value x less than 1, pi fourths for x equals 1 on the boundaries, and 0 for absolute value of x greater than 1. So one of the things we can do with this representation then is evaluate this interval. So if we let x equals 0, then the integral from 0 to infinity of sine alpha over alpha d alpha is equal to pi halves. Okay. So this represents taking this periodic function and then representing it in this other space. And then from there, rewriting it, excuse me, in order to evaluate potentially an integral that maybe doesn't have an easy or obvious solution. Okay. We can do this with the different forms as well, and we'll look at one example after you guys get a chance to set a problem up. Are you ready for a problem? Okay. All right. So, in class problem. And this is more of a setup. I don't want you to go all the way with this. So let's consider, where's my problem? We have f of x is equal to 1 for x between 0 and 1, and 0 everywhere else. So it's a bit of a shifted problem, right? So out to 0, then out to 1. Okay. What I want you to do is find g of alpha and then set up, but don't solve, f of x, all of this using the exponential expansion. or the exponential Fourier integral. So you're going to basically follow the same steps I did with this step function that's not symmetrical. Okay, this is essentially, what is it, 20.2.2 in your textbook. There, it makes more sense, and as does here, actually, to use the sine transform. But I want you to get used to using the exponential transform. You have another problem in the homework that looks at basically a triangle wave. Well, not wave, just a triangle, because it's not periodic. Everybody understand what they're supposed to do? All right, let's do this then. All right. Oh, Everything come out okay? Okay. Okay, hopefully people are able to follow the logic of this. To find g of alpha, we would do the same thing, 1 over 2 pi times the integral from minus infinity to infinity of f of x e to the minus I alpha x. In this case, that would be 1 over 2 pi times the integral from 0 to 1 times e to the minus I alpha x dx. So that would be 1 over 2 pi, 1 over minus I alpha times e to the minus I alpha x evaluated from 0 to 1. So that would be, depending on how you wrote this, you could write this as I over 2 pi alpha times e to the minus I alpha minus 1, or keep the I on the bottom and reverse that. So that's your g of alpha. Everybody get that, or something like it? Okay. Then your representation of f of x is just putting that back in. So this would be minus the integral from minus infinity to infinity of I over 2 pi alpha times, say, e to the minus alpha minus 1 times e to the I alpha x d alpha. All right, and then that's your integral representation of f of x. You could then, if you wanted to evaluate that, to use this as a method of evaluating a definite integral. The easier way and the more transparent way of doing this would be to take advantage of what this function looks like. So instead of an exponential, you'd use the cosine series. And if you use the cosine series, then it just turns out to be the integral of cosine, right? And then everything becomes pretty straightforward. And actually, as you might expect, the answer, if you want to evaluate the definite interval, is not that much different. And what I kind of slipped in here without really saying anything, if you notice the three different values when you do this this evaluation of the definite interval, encapsulate in them the Dirichlet condition from the Fourier series. In other words, there is a value in the middle, there's a value at the end, and the midpoint is equal to the average value of those two values, which is pretty cool. So that works even in this representation. Seems straightforward? Okay, one last example before I set you loose. And this is going to set up the reason why physicists love these transforms, right? So another example would be doing an analysis of a finite wave train, right? It'd be awesome if things were truly infinite, but they're not. So suppose we have f of t is equal to, say, sine of omega naught t for t less than some number of cycles, n. So n pi over omega naught, and 0 for t greater than that. Right? So you can think of this as something that looks like a sine. But that terminates, right? It might only have 5 cycles, right? Or n cycles, at least in this case, n cycles. All right, what are we to make of this? Since f of t is odd, that tells us we should evaluate, or looking at this, we should transform this using the sine interval, right? Rather than the exponential or the cosine. So to get to our interval, we use g sub s of omega. That's equal to the square root of 2 over pi times the interval from, say, 0, if we started at 0, times n pi omega naught, n pi over omega naught. Our function is sine omega naught t. The transform kernel is sine omega t dt. This should start looking familiar, right? This starts looking like resonance, right? So now if we are careful with this, we can write gs of omega is equal to square root of 2 over pi times, let's see, sine of quantity omega naught minus omega times n pi over omega naught. All of this over 2 omega naught minus omega. This is where we've evaluated this interval. Minus sine of omega naught plus omega times n pi over omega naught divided by 2 times omega naught plus omega. So for large omega and omega approximately equal to omega naught, g sub s of omega becomes the square root of 2 over pi times sine of omega naught minus omega times n pi over omega naught over 2 omega naught minus omega. And basically what this does for us is it takes this function in temporal space. And the transform then goes from time to omega. And what we end up with is something centered on omega naught where we have a peak. And then harmonics on either side where delta omega is equal to omega naught over n. That is the width of this peak. Okay. We can find what the zeros are. They're just basically omega naught minus omega over omega naught. So they're basically plus or minus 1 over n, plus or minus 2 over n, and so on. Right? So this is our g sub s of omega. So what I want you to realize, what we've done here is we've taken this finite train, right, and we've transformed it so that we've identified, even if we didn't know by looking at what this train was doing, what the most important frequency was, omega naught. Because it's finite, we still have harmonics. If basically the longer the train, the larger the n, right, this becomes more narrow, and there are fewer and smaller frequency or harmonics. And if n goes to infinity, then we would just have one spike at omega equals omega naught. Okay, and so this is the idea behind power series analysis using Fourier transform. And what you've probably seen in some labs, at least, is things like discrete or fast Fourier transform. So we can look at this data and pick out the important frequencies. Okay. This is also tied to things like Heisenberg uncertainty, right? When you're dealing with the wave nature of matter. Okay, I think I'm out of time. Are there questions before I let you go? No? All right. Next time, we will continue and look at further applications of Fourier transforms and then move on to Laplace transforms. Make sure you look over the solutions for homework 6. Get started on homework 7. And just to remind you, turn in homework 7. You can, the final is optional. That is, if you've turned in all of the homeworks, then if you like, you can take the final to improve your grade. It won't lower your grade. But if you like the grade where you're at, you don't have to take the final. You're done. Okay? All right. See you guys later.
Thanks, Meg.
Thank you.
Welcome. Bye.
Bye, Rick.
Bye, Adrian.